Welcome to a read along with Dr. Pell in the book Discrete Perspectives in Mathematics. This is subsection 4.4.3, the third intersection with the vertical. Okay, so currently we don't see any third intersection points. So we're going to change the way we're looking at this red curve a little bit so we can actually see the third intersection. There really is, but we're going to have to go up a dimension to see it. So we're going to think of this curve as being the intersection of two things. First of all, it's the intersection of this equation. If you were to graph it in three space with a z-axis, an x-axis, and a y-axis, so for different x and y values, if you plug those in, you could solve for a z value and get a point, and you can get a whole graph, a whole curve. So it's going to be the intersection of this surface even. This is a whole surface in three space, and this plane z equals 1. Notice when you set z equals 1 in this equation, it just turns out to be that one. So this is really the intersection between this this surface, which we can see in 3 dimensions, and this plane. The plane, so of all points that have an altitude of 1 or a z value of 1. Okay, so even if you aren't familiar with 3D graphing, yeah, that's just kind of what we discussed. Setting z equals 1, you get that curve. Okay, so let's look at a picture then. So the one in blue is actually the surface of this equation right here. All right, and this red is z equals 1. Now, okay, let's suppose that we take any point that's a solution to this. All right, so that means it's a point on this curve. So a point just on this curve here, like in particularly, you could think of it as AB comma 1 because it's a z value of 1, right? If it's going to be a solution to this curve, and then it's going to be a solution to this curve as long as we set z equals 1. So AB1 would be the full thing. Now notice in particular something interesting. If we multiply this solution by k, meaning component-wise, it's like we have AK, BK, K, and we plug it in here everywhere. So plug in AK, BK, K into this equation. Look what happens. The K's cancel everywhere, and we're left with this, which is the same thing as plugging AB in here, which means that this is actually a solution, which is interesting. We take a point and we multiply it by K. So if you take a point and multiply it by K, kind of what happens is, imagine K being 0. When K is 0, you're back at the origin, and as K goes up, it's like thinking of this as like a vector, and you're lengthening it out in a straight line as it goes up. And so really it's like a whole line. It's a whole line from the origin emanating, which represents, anything on that line is actually a solution. In fact, this whole blue surface is actually made up of lines like that. And the line hits and goes through, and each of those lines go through this curve, at least most of those lines. There's one line that doesn't, and that's kind of where we'll be going. Okay, so let's take a look at this. So for instance, see these green lines? These green lines are just examples. So this whole blue surface is actually, if we took all the lines through the origin that represented solutions to that solutions, actually this whole blue surface would just be green, full of all those going everywhere. It's just made up of these green lines. As we go. But there is an issue because all of these green lines actually intersect the plane z equals 1, except for one of them. So kind of what we're thinking is, so think of all the points on the curve as actually being these green lines. And all of them are apparent or pictured on the curve because they intersect it. All of them go through this except for one. So let's see, which one would that be? Okay, so in order to see this more clearly, here is a little here's a little demo or interaction that you can actually see, and we can actually see in this the point, and you can see it right here as well. So the y-axis actually itself lies in this blue surface. And see this red right here? The red plane right here represents z equals 1. Notice how this green line does not intersect the red plane. It's parallel to it. So this green line, the y-axis, actually represents a point on our elliptic surface, if you will, or elliptic curve, which is not seen in the red plane. So it's a point that's off. We call it the point at infinity. Here's another little description. So notice, well, why in the world is this? There's a plane right here. What is that? So a plane. So lines right now on the surface represent the points in on the curve, but planes like this, like a flat plane, when we intersect it with the red plane, we get a line. Oh my goodness! So lines are like planes, and points are like lines. So we're just kind of going up a dimension on each one. So kind of what we're looking at is we take a plane and cut the and cut this and cut it through that blue surface, and it should intersect. If it intersects, or if two of the green lines lie in this plane, then actually a third one will as well, when you take into account multiplicity. And that way, actually, look, we can actually add this this green line, which isn't even on the red plane, with other lines that actually you do see on that plane. So maybe a line here and a line there that kind of we can see appearing through this red plane, and added with, so we have three of them occurring there. So there really is a third intersection all the time. It's just sometimes, at least for the vertical ones, like here's a vertical line right here. Imagine that's the curve right there. Here's a vertical line. And this vertical line, you don't see any third intersection. However, if you thought of it in a plane, this plane actually comes and it hits. It actually goes right through the y-axis, which is below the plane z equals 1. So that's the third, and that's the third guy. Okay. So let's just take a minute and come up here and actually look at a visual of this right here. So we're gonna go there just a second here. Okay, so here we are. When we click on that, we come here and we can take a look and see kind of what's happening here. So here's the plane, z equals 1. All right, that's where the red one, and that's where the curve is. This green line right here is the intersection. And see this blue plane right here? This blue plane, it represents a line. So let's kind of look at this. So we have the curve here, and this blue coming through represents a line, and it goes through this point on the curve, and it goes through this point, and this point goes through 3 points on the curve. Each of these points is actually like a line. It goes to the origin. So you can kind of see those lines here. Maybe come on this side, see the lines. So you have a line coming this way through that point. You have a line coming up here and a line coming up here. So there's 3 different lines. These lines live in the blue surface, which is a generalization of that curve we see here. So the blue surface is the generalization, and these orange lines right here live in that live in the blue surface. So then, if we want to add, so notice that indeed there are 3 intersection points to the curve, and those 3 intersection points are actually 3 lines which live in both the blue surface and the plane that's passing through it. So we can kind of generalize this completely. Now also notice, look at this, see this y-axis down here? This y-axis is actually a line that lives in the, so this is the y-axis right here, see right here, right here. It's a line that lives in the blue surface, and it's a line that actually does not appear anywhere in this curve here, which is a cut of the blue surface by that curve. Now, if we were to draw a plane that cuts through a vertical line, and that, okay, so if we take a vertical line, that a vertical line right here, um, let's see, that passes from here to here. So all these planes, notice how this blue plane passes through the origin, just like all the lines pass through the origin. So let's just think about this. Think about a plane. So we're going to think of all these planes as passing, as well as the lines as passing through the origin, just like the blue surface does. So if we take a vertical line, then the plane it represents is actually the plane represented by that vertical line here in the plane z equals 1. And a point, which is the origin. Now, that actually is always going to intersect with the y-axis itself. So we would end up getting that going on, right? We would end up getting a third intersection, even though, at least in points, in point land, we can't see the third intersection. But if we beef up our viewpoint to another dimension, then we would see it, and we would see that that intersection going on. Okay, so this is kind of what we were thinking about right here. See this y-axis, and this plane that's cutting through is like one of those vertical lines, and it hits that. So we really do have a third intersection with the vertical. And okay, so we'll end this little video right here. The next one will be thinking about how to get an identity operation and where we should go with that. Thanks for watching.